All right, today we are going to pull back the curtain on one of the coolest, most beautiful secrets in the entire universe. We're about to see a hidden connection between two forces you deal with every single day, and it's one of the most elegant ideas in all of physics.
So let me just start with a kind of crazy question. What if I told you that one of the fundamental forces of nature, magnetism, isn't really a force of its own at all? What if it's just a trick of perspective? Just keep that idea in the back of your mind. You know, we all grow up learning about electricity and magnetism, like they're two completely separate things. In school, in our daily lives, they seem to play by totally different rules.
I mean, on one hand, you've got electricity, right? That's all the stuff like static cling, the power in our walls, lightning. It's all about charged particles pushing and pulling on each other. And then, on the other hand, there's magnetism. That's the mysterious force that sticks magnets to your fridge and tells a compass which way is north. They seem like totally separate players on the field.
Okay, so to see how these two are secretly connected, we're going to use a classic thought experiment. It's incredibly simple, but what it reveals is absolutely profound. All we're going to need is a wire with some current flowing through it and one little moving charge.
All right, let's set the scene. Here's our experiment from our point of view, what physicists call the lab frame. Basically, we're just standing still, watching. We've got a wire, and inside it are stationary positive charges and a whole bunch of negative electrons flowing along. That flow is our electric current. And flying right alongside the wire is our little test subject, a single positive charge.
So, if you were in a physics class, how would you break this down? Well, first off, the wire itself is electrically neutral. For every positive proton, there's a moving negative electron, so the charges cancel out. No net electric field. But, and here's the key, those moving electrons create a magnetic field that loops around the wire. And one of the fundamental rules of physics is that a magnetic field will push or pull on any other moving charge. In our case, that magnetic force actually pushes our little positive charge away from the wire. It repels it. Pretty straightforward.
But, and this is the big but, that whole explanation was from our perspective. What does the universe look like from the point of view of that tiny positive charge as it's zipping through space? Because here's the thing, the laws of physics have to work from its perspective too.
And to answer that question, we have to do something kind of wild. We have to jump into the frame of reference of the moving charge itself. And to do that, we need to bring in a little bit of help from Albert Einstein and his special theory of relativity. Now don't worry, it's way more intuitive than it sounds. No crazy math, I promise.
And check this out. This is where you can really see the magic happen. On the left, that's the world we just talked about, what we see in the lab. But on the right, that's the world from the charge's point of view. Notice how the spacing of the positive and negative charges in the wire looks totally different? Let's talk about why. The key that unlocks this whole puzzle is an amazing concept called length contraction. It's a cornerstone of special relativity, and it basically says this: the faster something moves relative to you, the shorter it appears to be in its direction of motion. This isn't some optical illusion. It's a real physical feature of how space and time work.
All right, so we've got this weird length squishing idea. How in the world does that explain what's happening to our charge? Well, it turns out that from the moving charge's perspective, the force it feels isn't magnetic at all. It's actually something way more familiar.
Let's walk through this one step at a time. First, imagine we're riding on that positive charge. From our new point of view, we're the ones sitting still. So that means the entire wire is rushing past us. Okay, so now the positive protons, which were stationary before, are moving backward. Because of length contraction, the distance between them seems to shrink. They look all bunched up. Now what about the electrons? Well, from our new perspective, they're actually moving much slower than before. This means the length contraction effect on them is way less, so their spacing seems to stretch back out to normal.
So what's the bottom line? From the charge's point of view, the positive charges are now packed together more tightly than the negative charges are. There are more protons per inch than there are electrons per inch. So get this, the wire, which looked perfectly neutral to us in the lab, now appears to have a net positive charge. And this slide just lays it all out crystal clear. From our point of view in the lab, we see a neutral wire creating a magnetic force. But from the charge's point of view, it sees a positively charged wire creating a simple electric force. Two completely different explanations, but look at the outcome. In both cases, the positive charge is repelled. The physics works out perfectly, no matter how you look at it.
So you see, this isn't just some clever party trick. This is a huge deal. It's a profound revelation about the fundamental fabric of our reality. It's telling us that electricity and magnetism aren't two separate things. They're one.
That thing we call the magnetic force, it's not its own special force. It is literally just the electric force seen from a different, moving point of view. It's a relativistic effect. They are two sides of the exact same coin, a single, unified force we call electromagnetism.
You know, one of our sources just puts it perfectly with this quote. From its own perspective, a charge is always at rest. It's never moving with respect to itself, right? That means it can only ever feel electric forces. The whole idea of a magnetic force is just a label we observers invented to make sense of that same event from our moving point of view.
And that just leaves you wondering, doesn't it? If something as real and fundamental as one of the basic forces of nature turns out to be just a matter of perspective, well, what else that we take for granted as real is just waiting for us to look at it from a different angle.